Welcome to this video. Today, we're diving into LeetCode problem number 908, titled Smallest Range I. This is a fascinating problem that challenges us to manipulate an array and determine the smallest possible range of its values. We'll explore the solution step by step, covering the key concepts and approaches. Let's get started. The problem asks us to work with an integer array called nums and a given integer k. We can perform an operation on any element in the array where we either add or subtract the value of k. For example, if an element in nums is 5 and k is 3, we can adjust this element to any value between 2 and 8, since 5 minus 3 gives 2, and 5 plus 3 gives 8. The goal of the problem is to calculate the smallest possible range of the array after applying this operation to each element. The range of an array is defined as the difference between the largest value and the smallest value in the array. Our task is to minimize this range and return it as an integer. Let's look at a few examples to better understand the problem. In the first example, we are given nums as an array with a single element, 1, and k is 0. Since there is only one element in the array, the range is naturally 0, regardless of any operations. There's no other value to compare it to, so the output is 0. This example highlights that if the array has only one element, the smallest range will always be 0. In the second example, the input array is nums equals 0, 10, and k equals 2. Here, the element at index 0, which is 0, can be adjusted to any value between -2 and 2. Similarly, the element at index 1, which is 10, can be adjusted to any value between 8 and 12. By analyzing the adjusted ranges, the smallest possible range of the array occurs when the values overlap or are as close as possible. The minimum value in the adjusted array is 2, and the maximum value is 8, so the smallest range is 8, 2, which equals 6. In the third example, we have nums equals 1, 3, 6, and k equals 3. Here, the first element, 1, can be transformed into any value between -2 and 4. The second element, 3, can be adjusted to values between 0 and 6. The third element, 6, can be transformed into values between 3 and 9. When we examine these ranges, we find that there is a complete overlap at the value 3. All elements can adjust to fall within this overlap, resulting in a range of 3, 3, which equals 0. This example demonstrates that overlapping ranges can lead to the smallest range of 0. To summarize, the problem can be reduced to finding the smallest possible range after adjusting both the minimum and maximum values in the array by k. Specifically, the adjusted minimum is calculated as min, nums, plus k, while the adjusted maximum is max, nums, k. If the adjusted maximum is less than or equal to the adjusted minimum, the range is 0. Otherwise, the range is simply the difference between the two. Once the minimum and maximum values are determined, the result can be calculated in constant time, O(1). Since finding the minimum and maximum of the array takes O(n) time, the overall complexity of the solution is O(n). To solve the problem of finding the smallest possible difference between the maximum and minimum values of the array nums, after modifying each element within a range of k, we first consider a brute force approach. The intuition here is to exhaustively simulate all possible transformations of the array. For every element in nums, we generate all values in the range, number plus k. By doing this, we can calculate the new minimum and maximum for every combination of transformed values, and ultimately determine the smallest difference. However, this approach is computationally expensive. The number of possible transformations grows exponentially with the size of the array, resulting in a time complexity of O(2k)(n). While it gives a complete exploration of the problem, it is impractical for larger inputs due to its inefficiency, making it more of a theoretical exploration than a feasible solution. Now, let's focus on an optimized approach that leverages the constraints of the problem. Instead of simulating all transformations, we recognize that the smallest difference is determined only by the maximum and minimum values of the array. If each element in the array can shift within the range, number plus k, the maximum value can decrease by k at most, and the minimum value can increase by k at most. This observation leads us to calculate the new difference as max, nums, k, min, nums, plus k. Importantly, if this value becomes negative, the difference is 0 because the values overlap completely. This can be expressed concisely with the formula max 0 max nums min nums 2 asterisk k. The complexity of this approach is linear, O(n), since calculating the maximum and minimum of the array only requires a single pass. This method avoids the inefficiency of brute force while directly addressing the problem's constraints, making it far more practical. Given the options, the optimized approach is the clear choice due to its simplicity and efficiency. By focusing solely on the maximum and minimum values of the array, we eliminate unnecessary computations. A key insight here is that when 2 asterisk k is greater than or equal to the difference between the maximum and minimum values of the array, the range of possible values completely overlaps, resulting in a zero difference. On the other hand, if the overlap is smaller, the result is simply the difference after accounting for the shifts of k in both directions. This realization was the aha moment in developing this solution, understanding that the transformation range, number plus k, effectively shifts and overlaps the array. The formula max 0 max nums min nums 2 asterisk k succinctly captures this logic, making the optimized approach not only effective but also elegant in its simplicity. Finally, let's compare the trade-offs between the two approaches. The brute force method, while exhaustive and comprehensive, is prohibitively inefficient for larger arrays due to its exponential time complexity. It is only feasible for very small inputs, and even then, it lacks the elegance and practicality of the optimized method. On the other hand, the optimized approach is highly efficient, scaling well for large inputs while maintaining correctness. The key trade-off here is that the optimized solution requires an understanding of the problem's constraints to directly derive the formula, but once that insight is gained, the implementation is straightforward. In conclusion, the optimized approach is the superior choice, balancing efficiency, simplicity, and correctness to solve the problem effectively within the given constraints. To approach problem number 908, smallest range I, we need to determine how to minimize the range of an array after modifying its elements. Specifically, we can adjust each element in the array nums by adding or subtracting a value k. The key is to find the smallest possible difference between the maximum and minimum values of the modified array. First, let's identify the maximum value, max_val, and the minimum value, min_val, in the array. Without any modification, the range is simply max_val, min_val. However, after applying the allowed adjustments, the new maximum value can be at most max_val k, and the new minimum value can be at least min_val plus k. This gives us the formula for the new range, max 0 max_val k min_val plus k. Using max 0 ensures that the range does not go below 0, which would happen if the values overlap completely after modification. The formula max 0 max_val k min_val plus k captures the adjusted range after applying k to each element in the array. To implement the solution, the algorithm follows these steps. First, find max_val and min_val in the array, which requires a single pass through the array in O(n) time. Second, calculate the initial range as max_val min_val. Third, adjust the range using the formula, and finally, return the adjusted range as the output. Importantly, we do not need to explicitly modify the elements of the array to calculate the result. Instead, we directly compute the potential maximum and minimum values after adjustment. This optimization reduces both the time complexity and memory usage, making the algorithm highly efficient. It's worth noting two important insights about how the range reduction works. First, if the initial difference, max_val min_val, is less than or equal to 2 asterisk k, the gap can be completely closed, resulting in a range of 0. However, if the difference exceeds 2 asterisk k, the range can only be reduced by a maximum of 2 asterisk k. This is because the adjustments made to the maximum and minimum values are limited by k. There are also specific edge cases to consider. For example, if the array has only one element, the range is always 0 since the maximum and minimum are the same. For large k values, where k is sufficient to close the gap between max_val and min_val, the range also becomes 0. On the other hand, if k is small, the range reduction may be minor. From a data perspective, the only critical information we need is the input array nums, from which we derive max_val and min_val. This ensures that our algorithm runs in O(n) time and uses constant space. Let's analyze the complexity of this approach to confirm its efficiency. The time complexity is O(n), as finding max_val and min_val requires just one iteration through the array. The range adjustment calculation is a simple constant time operation, O(1). Thus, the overall time complexity is O(n). In terms of space complexity, we only use a few variables such as max_val and min_val, resulting in constant space usage, or O(1). No additional data structures are needed. The pseudocode for this solution is straightforward. We define a function smallest range I that takes nums and k as inputs. Within the function, we compute max_val and min_val using Python's built-in max and min functions. Finally, we return the adjusted range using the formula max, 0, max_val, k, min_val plus k. This simplicity makes the algorithm not only efficient but also easy to implement. This algorithm is both efficient and robust, handling edge cases gracefully. Let's walk through an example to see it in action. Consider the input nums equals 1, 3, 6, and k equals 2. First, we determine the maximum value, max_val equals 6, and the minimum value, min_val equals 1. The initial range is 6, 1 equals 5. Next, we adjust the range. The maximum value after modification is max_val, k equals 6, 2 equals 4, and the minimum value after modification is min_val plus k equals 1 plus 2 equals 3. The new range is max, 0, 4 to 3, equals 1. Thus, the smallest possible range after adjustment is 1, which is the final output. This example demonstrates how the algorithm efficiently calculates the result without modifying the array, while fully utilizing the given constraints. This Python implementation solves LeetCode problem number 908, smallest range I. The goal is to minimize the range of the array after modifying each element by adding or subtracting a given value k. The solution begins by identifying the maximum and minimum values in the input list nums using Python's built-in max and min functions. These values represent the extremes of the range that we want to minimize. Next, the code calculates the new potential difference after applying the k adjustments. Specifically, the maximum value is decreased by k to minimize it, and the minimum value is increased by k to maximize it. The difference between these adjusted values gives the new range. Since the range cannot be negative, the code ensures the result is non-negative by taking the maximum of the calculated difference, new_diff, and 0. This ensures that if the difference becomes negative, e.g., when the adjustments make all elements equal, the result is clamped to 0. The solution is efficient with a time complexity of O(n), where n is the length of the input array nums, because finding the maximum and minimum values in an array requires a single pass. The space complexity is O(1), as no additional data structures are used. This implementation is concise, handles all edge cases, e.g., when the array has only one element or when k is very large, and adheres to the problem constraints. This is the Java implementation of LeetCode problem number 908, smallest range I. The logic mirrors the provided Python solution. Key differences include explicit type declarations, the use of a for each loop to compute the maximum and minimum values, and the use of Java's math library for operations like max. The result calculates the range difference after applying the given transformation, ensuring the output is non-negative. In this problem, we are given an array of integers called nums and another integer k. The task is to modify each element in the array by adding or subtracting any value within the range, k, and then determine the smallest possible difference between the maximum and minimum values of the modified array. To solve this, we first identify the maximum and minimum values in the array, calculate their difference, and then adjust that difference based on how much we can modify the values using k. For instance, in the example where nums equals 1, 3, 6, and k equals 2, the first step is to find the maximum and minimum values of the array. Here, the maximum value is 6 and the minimum value is 1. Next, we calculate the initial difference between these two values, which is 6, 1, resulting in a difference of 5 before any modifications are applied. Now, to adjust the difference using k, we recognize that each value in the array can be modified by up to k in both directions. This means we can reduce the maximum value by k and increase the minimum value by k, which allows us to reduce the difference by as much as 2k. In this example, adjusting the maximum and minimum gives us 6 to 2 for the maximum and 1 plus 2 for the minimum. Subtracting these values results in a new difference of 4, 3, which equals 1. Finally, since the difference must always remain non-negative, we take the maximum of this new difference in 0. Here, the result is max 1, 0, which is 1. Therefore, the smallest possible difference for this example is 1. Let's consider a different example where nums equals 5, 5, 5, and k equals 10. In this case, all the elements in the array are the same, so the maximum and minimum values are both 5. The initial difference between these values is 5, 5, which equals 0. Even if we modify the maximum and minimum values using k, the difference remains unchanged because all elements are identical. Specifically, if we compute the adjusted difference, we get 5 to 10, 5 plus 10, which equals -5, 15, resulting in -20. However, since the range cannot be negative, the result is set to the maximum of -20 and 0, which is 0. Thus, for this example, the smallest possible difference is 0. Now, let's analyze a more complex example where nums equals 2, 7, 10, 15, and k equals 5. Here, the maximum value in the array is 15, and the minimum value is 2. The initial difference between these values is calculated as 15 to 2, which equals 13. To adjust this difference using k, we reduce the maximum value by 5 and increase the minimum value by 5. This gives us 15 to 5 for the maximum and 2 plus 5 for the minimum. Subtracting these values results in a new difference of 10 to 7, which equals 3. As always, we ensure that the difference is non-negative by taking the maximum of the new difference in 0. In this case, the result is max 3, 0, which is 3. Therefore, the smallest possible difference for this example is 3. To summarize, there are a few key insights to keep in mind for this problem. First, the maximum reduction in the range of values is 2k, since we can decrease the maximum value by k and increase the minimum value by k. Second, if the adjusted difference becomes negative after applying k, the result is set to 0 because the range cannot be negative. Lastly, the solution is highly efficient, as it only requires us to calculate the maximum and minimum values of the array, making it run in O(n) time. Additionally, it uses a constant amount of extra space. These properties make the solution both simple and optimal for this type of problem. To analyze the time complexity of this solution, we start by looking at how the maximum value in the array is found. The max function scans through the entire array, comparing each element to determine the largest value. This requires n comparisons, where n is the size of the array, resulting in a time complexity of O(n). Similarly, the min function performs a full scan of the array to find the smallest value, again requiring n comparisons and contributing another O(n) to the overall time complexity. After obtaining the maximum and minimum values, all the subsequent operations, such as subtraction, addition, and evaluating max, new_diff, 0, are constant time operations that do not depend on the size of the input. Therefore, the combined time complexity of these operations is O(1). When we sum up these components, the total time complexity is determined by the two linear scans of the array and the constant time operations, which simplifies to O(n). Adding together the components we just discussed, the total time complexity is O(n) plus O(1), which simplifies to O(n). Now, for the space complexity, we consider the memory usage of the algorithm. The solution does not rely on any additional data structures that grow with the size of the input. Variables like max_number, min_number, and new_diff are scalar values, meaning they occupy a fixed amount of memory, regardless of the size of the input array. Moreover, the algorithm does not modify or duplicate the input array nums, so no extra space is allocated for the input. Taken together, the space complexity is constant, or O(1), because memory usage remains fixed and independent of the input size. This makes the solution both time efficient and memory efficient. To better understand the efficiency of this solution, let's compare it to a brute force approach. A naive way to solve this problem might involve iterating through all possible values of each element in the array after applying k or plus k. For each configuration, we would then recompute the range of the array. This approach involves generating all possible combinations of modified arrays, which grows exponentially with the size of the input. Specifically, for an array of size n, the time complexity would be O(2 to the power of n, making it infeasible for larger inputs. In contrast, the solution provided here avoids this exponential growth by focusing directly on adjusting the maximum and minimum values of the array. By leveraging this insight, the solution achieves a linear time complexity of O(n), as it only requires a single pass to compute the max and min values. The space complexity remains O(1), because no additional memory proportional to the input size is required. This optimization makes the solution significantly more scalable and efficient. Now, let's analyze the algorithm in terms of its best, average, and worst-case scenarios. Regardless of the specific input, the algorithm always performs a full scan of the array to compute the maximum and minimum values. This means the time complexity remains O(n) in the best, average, and worst cases. The performance does not depend on the order or values of the elements in the array, as the linear scan is always required. To summarize, the time complexity of this solution is O(n), where n is the size of the input array, and the space complexity is O(1), as no additional memory proportional to the input is used. Compared to the brute force approach, which has an exponential time complexity of O(2 to the power of n, this solution is optimal, both in terms of time and space efficiency. It effectively balances simplicity and performance, making it a robust choice for this problem. When tackling this problem, there are several common mistakes to watch out for. First, some people miss the scenario where the difference between the maximum and minimum values is already less than or equal to 2 times k. In this case, the smallest range is 0 because you can adjust all elements to the same value. Another error is overcomplicating the solution by trying to individually adjust each element in the array. Remember, the problem only requires analyzing the maximum and minimum values. You don't need to iterate through every element. Additionally, edge cases are often overlooked. For example, if the array has just one element, the range will always be 0 since there's no variability. Similarly, an array with all identical elements also results in a range of 0, regardless of the value of k. Finally, some misunderstand the flexibility of k, thinking it must be applied uniformly to all elements. Instead, each element can independently vary by any amount between k and k. Another subtle issue to be mindful of is integer overflow in languages like C++ or Java. If the input values are very large, failing to account for this can result in incorrect calculations. Now, from an interview perspective, the core insight here is focusing on the relationship between the range of the array and the flexibility provided by k. Rather than getting caught up in every element, the emphasis should be on the extremes, the maximum and minimum values. This problem is a good example of pattern recognition. It highlights the importance of simplifying the array to its key properties, like the max and min, instead of processing each element individually. Moreover, interviewers often expect you to work toward an O(1) solution after determining the max and min in O(n). Avoid any unnecessary computations to meet this expectation. This problem is closely related to several others on LeetCode, which are worth exploring to deepen your understanding. For example, problem number 910, smallest range 2, introduces a more complex variation where the adjustments are made differently, requiring a recalculation of the smallest range. Problem number 462, minimum moves to equal array elements 2, involves minimizing the range of differences, but with the constraint of making all elements equal, which is conceptually different. Another related problem is number 1984, minimum difference between highest and lowest of k scores, which focuses on selecting a subset of elements to minimize the range. Finally, problem number 1509, minimum difference between largest and smallest value in 3 moves, explores minimizing the range with a limited number of allowed adjustments to the array. Each of these problems builds on similar concepts but introduces unique constraints and variations. There are also alternative approaches to consider, though they come with trade-offs. A brute force solution, for instance, involves iterating through all possible adjustments to the elements. While this method can help build a conceptual understanding of the problem, it's computationally expensive (n squared), or worse and impractical for larger arrays. Sorting the array and analyzing possible ranges is another approach. While unnecessary for this problem, it can be useful in related problems like number 910. However, sorting adds n log n complexity, which makes it suboptimal here. Lastly, the two-pointer technique is a powerful tool for range-related problems, especially in scenarios involving subsets or sliding windows, such as in problems number 1984 and number 1509. While not required for this specific problem, it's good to keep in mind for extensions or more complex variations of range minimization challenges. Great job! We've just solved LeetCode problem number 908, smallest range I. This problem reinforced key concepts like array manipulation and optimization. Remember to think through edge cases and constraints when solving similar problems. Thank you for tuning in. Be sure to like, subscribe, and share for more content like this. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!